Welcome to 37th lecture in the course of Industrial Engineering and Operations Research. We are discussing operations research, and in that we are discussing linear programming, and I just started dual problems. So, in the last class you saw that I told you how to obtain dual problem from primal problem. But in this class I want to discuss some properties of the dual problems. So, let us see the property 1, very important. At any simplex iteration of the primal or the dual objective coefficient of variable j in one problem is equal to left hand side minus right hand side of constraint j in the other problem. So, at any simplex iteration of the primal or the dual, okay, that means at any this much you say that. So, I am telling objective coefficient of variable j in one problem. Suppose there is some variable j, corresponding to that there will be some constraint in the other. So, in the constraint you say left hand side minus right hand side of the constraint, this becomes equal in the other problem, okay, that is what. So, also remember dual of the dual is primal. This is very obvious that if I make a there is a primal and I make its a dual, again I make dual's dual, it will become again primal. So, it will be, so what is the advantage in that? And as we have already seen that there, since there is a correspondence, so number of variable in one problem is equal to number of constraint in the other problem. Suppose there are 5 variables in one problem, then in the primal, then they will become constraint, okay, and vice versa. So, it will be computationally efficient to solve a problem with less number of constraints. So, suppose I have got some problem, there are only 2 variables in primal, okay, and but there are 50 constraints. So, if we have 50 constraints, that means so many lines will be there. In simplex table, you will get 50 rows and you have 2 variables. So, you have to do lot of computations, but you can make a dual of it. So, dual will have 50 variables, it will get interposed and 2 constraints only. So, you can easily solve that. You will reduce the computations because only 2 rows of the simplex table will be there. Variables have increased, but the constraints have reduced. So, like that you have this thing. So, you get advantage computationally, and sometimes you may get this situation also, that suppose you have got 50 variables and 2 constraints. If you want to solve by graphical method, then you convert into primal. So, you will have only 2 variables and 50 constraints. So, this can be, although you have to make 50 type of lines in graph, but still that you know at least you can solve that 50 variable problem, you cannot solve graphically. So, there are advantages, okay. And property 2 is that how you can solve, because the beauty is that for any pair of feasible primal and dual solutions for anything, objective value in the maximization problem will be less or equal to objective value in the minimization problem. So, that means maximization problem will be less or equal to, and equality holds at the optimum. So, that means maximization problem is trying to, in maximization problem we are gradually increasing like this, okay, and in the minimization problem we are reducing slowly the value of objective function f. So, at one point they will both meet. So, that means if you have optimum solution, then both will give the same solution. So, you solve one problem or the other solution, final answer will be same, okay. So, this is a big advantage, okay. So, what happens that suppose you have problem minimize z is equal to 40 y1 plus 24 y2 plus 10 y3 and subject to these 2 constraints, that means y1 plus 3 y2 plus y3 is greater or equal to 2 and 3 y1 plus y2 plus y3 greater or equal to 5, and this is y1 greater than 0, y2 greater than 0, y3 greater than 0. So, by solving the dual form using simplex method, find out the minimum value of z and corresponding y1, y2 and y3, which are the active constraints of primal problem, okay, which are the active constraints of the primal problem, that is a question, and find out the unit worth of active constraints. They are asking unit worth. So I jump that, I tell you that suppose we make a dual problem, and if I associate x1 here and x2 here, so x1 x2 will be basically unit worth of resources. Okay, so let us say, so dual form, first make the dual form. So you see, minimize z is equal to this much, so its a dual will be maximized, w is equal to 2x1 plus 5x2, okay, 2x1 plus 5x2, and subject to is it is smaller than type sign. So y1's coefficient, I should see y1's coefficient, x1 plus 3x2 is smaller or equal to 40, 3x1 plus x2 is smaller or equal to 24, x1 plus x2 is smaller or equal to 10, and x1 greater than 0, x2 greater than 0. Now we, in order to solve that, we can introduce slack variables to convert the dual form into a standard one. So therefore we introduce x3 plus x4 plus x5, that means first becomes this, second becomes x4, this one x4 is the slack variable, and this is x1 plus x2 is smaller than 10, that means you can say x1 plus x2 plus x5 is equal to 10, where x5 is a slack variable, and x1, x2, x3, x4, x5 will be greater than or equal to 0. So therefore this type of thing is there, and you got this problem. Okay, so then you can naturally solve this problem. Okay, this can be solved by graphically also, by LP also. Let us do it by LP. Okay, W, I am solving dual problem only. So first is 2x1 plus 5x2. So I say x1 below that minus 2 minus 5 0 0 0 like that. x3's coefficient, x3 becomes the natural slack variable, x4 becomes slack, x5 becomes the basic variable. So x3, x4, x5. So in x3 row, these are the coefficient 1 3 1 0 0 40, 3 1 0 1 0, x5 is equal to this much. Okay, so we go to the, we see the most negative value because we are doing in the, we are dual problem is maximization. So we have to consider most negative coefficient. Most negative is x2. So x2 becomes the entering variable. So this becomes the pivot column. So now we find out the ratio. In the x3 row, it is 40 by 3, that means something 13.33. This is 24 by 1, okay, and this is 10 by 1 is equal to 10. So the least one is basically, least ratio is x5. So this becomes leaving. So instead of x5, now we bring x2, and I have got 1 1 0 0. Here already the coefficient of x2 is 1. So therefore there is no need to do any normalization, let it be like that, but we ensure that above it everything becomes 0. So that means if I multiply this x2 row by 5 and add in the objective function row, so this becomes 0 and this becomes 3, and this is similarly I multiply it by 3 and subtract in x3 thing, so you get this, and similarly I multiply by 1 only and subtract in x4, I get 0. So these things have become 0 in the pivot column, and you have got, that means you did row operation. So here you got W is equal to 50, you see that automatically. Now x1's coefficient is positive, so everything is positive, so you cannot make any variable entering variable, that means optimization has reached. So therefore we got the optimal solution. x1 is equal to 0 because it is not there, x2 is equal to 10 because it is there in this one, that means x2 is equal to 10, and of course x3 is something, x4 is something, but this is not the part of objective function. This from our side we added slack variables, and maximum value has come basically 50. So that means maximize W is equal to 5 into 10. Okay, so that means it is obviously 50 from there, 5 into 10. So you have got since maximum value is 50, so therefore in primal problem minimum value also must be basically 50. Okay, so that is what I want to say. In the dual problem, the optimal value of the slack variables in the objective function correspond to the values of the primal variables, that is y1 equal to 0, y2 equal to 0 and y3 equal to 5. Okay, so that is also one point. Optimal values of the slack, that means here basically correspond to the values of the primal in the objective function row. So in the objective function row you have got this one slack and surplus. So you have got, suppose this one x3 you have got 0, okay. So therefore y1 is equal to 0, and here you have got x4, this you have got 0, okay, coefficient. So therefore y2 is equal to 0, and similarly in the primal, and similarly here x5 is equal to 5. So therefore y3 is equal to 5. How I am telling that? It is by property 1, because corresponding to x3 we have y1 greater than 0, corresponding to x3 means we have this one. So we have got y1 greater than 0, okay, there. So hence 0 is equal to y1 minus 0. Corresponding to x4 we have constraint y2 greater than 0 in the other problem. So hence you have 0, y2 minus 0, and corresponding to x5 we have y3 greater than 0, therefore 5 is equal to y3 minus 0. So the primal constraint y1 plus 3y2 plus y3 greater than 2, it is corresponding to dual variable x1, okay, is inactive, since x1 is equal to 0, because it is an inactive, so therefore it is basically inactive, okay. So that is what you have said. And primal constraint 3y1 plus y2 plus y3 greater than 5, that means second constraint, which corresponds to dual variable x2 is active, since x2 is equal to 10, okay. So the unit worth of active constraint 3y1 plus y2 plus y3 greater than 5 is x2, that means 10, which is corresponding dual variable value, okay. So similarly you can have another type of problem. Suppose you have maximize z is equal to 2x1 plus 3x2 plus 6x3. Now subject to x1 plus x2 plus x3 is equal to 1, 2x1 plus 3x2 is equal to 1, and x1 greater than 0, x2 greater than 0, x3 greater than or equal to 0. So here how to make that this one? Suppose you make that this one, I want to make a dual form, okay. I can do in a very shortcut way, but for you I am just telling that proper procedure. Suppose I say make it standard form, that constraint should be written in standard form. So x1 plus x3 is equal to 1, no change here. 2x1 plus 3x2 is equal to 1. Oh, it is already in the standard form, nothing is to be done. So simply what we have to do, that it is already in the standard form, because it is equal to this one. So only thing is that I associate y1 with this constraint and y2 with this constraint, okay. And then I say instead of maximize we say minimize, instead of z we say w, and then I could say y1 into 1, because total quantity of resource is 1, x1 plus x2 plus x3 is equal to 1, that means resource is 1. So y1 into 1 plus y2 into 1, so y1 plus y2. So this is objective function, and subject to I have to write constraints. So corresponding to each variable in primal you will get one constraint. So here it is x1, so therefore it will be y1 plus 2y2, okay, that means 2y2, here x1's coefficient is 2, and it should be greater than or equal to, because with minimization here there will be greater than or equal to sign, greater than or equal to 2, because coefficient of x1 is 2. And then y1, why y1? Because x2's coefficient is 1 here, then x2's coefficient is 3, so 3y2 greater than or equal to 3, so the greater than. Similarly now corresponding to x3, so corresponding to x3 we have y1 here, and in x3 is not there in the second one, so you leave that. So y1 is greater or equal to basically 6, okay. So y1 is greater than or equal to basically 6. And then here after writing, because these were in the equality type of sign, so therefore what happens, that here we have to say that minimize, and probably we have to say that as per our rule that y1, y2 and y3, y1, y2 unrestricted, okay, because they are in that form. So we have to say that they will be unrestricted. So correct way is to say that. Later on if you say that y1 greater than 6, that is okay, but you have to say y1, y2 are unrestricted, and this is how that it has to be completed, okay. So this is what the type of this one has said, okay. So this is that type of thing has come y3. So, you are getting basically 3 variables, okay, x1, x2, x3. So, you are getting 3 constraints here. Okay. So, now what happens that you can actually try to solve them also, the graphically you can solve that, actually minimize, you say y1 plus y2, okay, this is this one y1 plus 2 y2, y1 greater than 6. Okay. So, you can, if you want to solve it graphically, then you can say y1, okay, I have taken the help of that for drawing the graph, the a2zmath.com, okay, but this is I am doing graphically, so it just gives x1, but this is basically y1 and this is basically y2. So, one constraint is that y1 greater or equal to 6. So, that is why you are getting one y1 greater, that means you have to be on this side, and on this side you have these type of constraints, that means y1 plus 2 y2 is equal to 2 line you have opened, okay, and then y1 plus 3 y2 greater than 3, that one also you have made, but it is showing this side, and but another constraint says that it has to be greater than this one 2. So, that means these two things immaterial, that means they are redundant type of things. Basically, you can be only in this zone, because this fellow says okay, you can go here, here, you can go here, 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 because y1 plus 2 y2 greater than 2. So, therefore, it is basically this one. So, therefore, ultimately the value of the objective function at each of these extreme points you have to find. So, extreme point is only 6 0, because only this thing only is there, other things you cannot do that. So, therefore, what happens that and lines through this one. So, objective function value is basically x1 plus x2, that means 6. So, the minimum value of the objective function occurs at the extreme point 6 0, that is all. Hence, the optimal solution becomes basically x1 basically y1 in our this one, because I use that software. So, therefore, x1 is equal to 6 y2 and minimum value is z is equal to 6. So, if the minimum value here is z is equal to 6, there the maximum will also be that 6. Unit of resource, worth of resource 1 is equal to 6 and worth of resource 2 is equal to 0. Okay. So, that means corresponding to that you can find out that unit worth of resource. Okay. That means because y1 is 0, so therefore, that worth will be resource. So, this is what that y2. So, this is you can actually see that y1 is equal to 1 and y2 is equal to 0. So, unit worth of resource corresponding to that constraint will be 0, because y1 and y2 are giving basically the unit worth of resource. Okay. Unit worth of resource of this is y1 and unit worth of resource of 2x1 plus 3x2 is equal to 1 is the y2. Okay. So, that means this is the thing. And now, property 2 means that final value, that minimization value is in one problem is equal to maximization value in other problem. This can be proved a bit very easy proof, okay, mathematically also. So, I just thought that I can show to you, but it is not that important for you. You can, because you are focusing more on application. So, suppose you have primal problem minimize CTX and subject to Ax is equal to B, x greater than or equal to 0. This is the standard form of the primal problem. Now, just see the dual form is what? Maximize YTB and subject to YTA is smaller or equal to CT. Okay, that much. But Y is unrestricted. I am not writing. If I have not written also, you have to understand that Y is unrestricted, because this is the problem. If you have equality type of sign, then this is the way. So, it is Y is unrestricted. Okay. Now, what I am telling that there is some lemma, if x and y, okay, not any, x and y are feasible for primal and dual respectively, then CTX will be greater than or equal to YTB. Okay. CT means minimization thing. So, proof. So, we have YTB is equal to YTAX, because B is equal to AX here. So, YTAX and YTAX, Y dot YTA is smaller than CT. So, therefore, it will become, this is basically CTX. Okay. So, it will, I have put CTX. So, therefore, YTAT is equal to this one. So this is true because x is greater than or equal to 0. So this is done. So this is the proof is that simple. Now I am just telling that one thing is popular by the name of duality theorem. Okay. So duality theorem says that if either of primal and dual has a finite primal optimal solution, so does the other. If primal and dual any one, suppose primal has a finite optimal solution, its value is say 50 or its value is 100. So naturally there is a solution for dual problem also, and the corresponding values of the objective functions are equal and both will be equal. But if the either problem has unbounded objective, suppose primal has got unbounded, therefore the other problem has no feasible solution. So if one is unbounded, other gives no feasible solution. This is called duality theorem. Okay. You can just understand it through example. Maximize z is equal to 2x plus 3y subject to x minus 4y is smaller than 10, xy greater than 0. I have given deliberately this type of problem. You can see that this is unbounded. Why? Because I am telling x minus 4y should be less than 10. So I can take y very large. I can take y is equal to 1 crore also. I can take y is equal to 50 million and it will be less than 10. So I can take y as much as I want. You can take a very big value of y without violating constraints. Y can be rather approach infinity. So it is unbounded, hence z will become unbounded. Now let us make a dual problem. How should I make the dual problem? For making the dual problem, let me write in the standard form. So x minus 4y plus s is equal to 10. Okay. Now I write in this one. So corresponding to this, let us say I am making dual problem. Okay. So dual problem corresponding to that, let me use y dash. Okay. Corresponding to that, let me use y dash. Okay. So this is okay. Y dash. Okay. So what happens that I will say that let us make first write in standard form. Okay. I am writing z is equal to 2x plus 3y plus 0s. Okay. That means I have written 0s. Okay. Subject to x minus 4y plus s is equal to 10. That's what I have written. Where s is a slack variable, notice that right hand side is positive, I have put. And xys will be greater than or equal to 0. Then what should I do that? Very easy, associate with this some dual variable. By what I will be indicating the dual variable? Maybe by w maybe. Okay, let us see. So I said minimum, no, w will be final. Let us indicate by t. Okay, associate t variable here. So minimize w is equal to 10t and subject to now coefficient t is greater than 2 corresponding to x. So t is greater than 2 corresponding to minus 4t greater than 3. T is greater than 0. However, t greater than 2 and minus 4t greater than 3 cannot be satisfied together, because you cannot have, because minus 4t greater than 3 means t should be smaller than minus 3 by 4. So one fellow says that t should be smaller than minus 3 by 4, other fellow says that t should be greater than 2. So naturally this is infeasible problem. So that's why that it has become this one. So it is true that in one problem if the solution is unbounded, in the other problem it will be infeasible. Okay. So that is this much only for today, and we will continue in the next class. Okay. And we will tell some more interesting things about the problem. Okay. Thank you very much.